this video, I'm going to show you an example of taking data from a tension test and using it to calculate some of our major material properties. So this is from the book, first problem, problem 8-1, and it says that a tension test was performed on a steel specimen having an original diameter of 0.503 inches. Let's write that down. We might need that later. Initial diameter of 0.503 inches and a gauge length, that's like our L sub 0, L naught, of 2.00 inches. And then the data is given in the table. In a tension test, we measure force. In this case, it's given to us in kips. And we measure the elongation of that gauge length. That's like your delta L in inches. We're asked to plot the stress strain curve and then to calculate things like modulus of elasticity, yield stress, ultimate stress, and fracture stress. We are not going to do this 1 inch equals 20 KSI scale thing. That would be for if you were doing this on graph paper, but I think we may as well use modern engineering tools like apps and software to do this. So I'm going to do this in Excel. Feel free to do these in MATLAB or whatever software you prefer. So I'm going to toggle over to Excel, where I've already put in that load and elongation. And let me put in our diameter was 0.503 inches. And our gauge length that we were given was 2 inches. So what I need to do next is calculate strain, which is dimensionless, and stress, which the way I'm going to do it will be in units of KSI. And the only reason I'm doing strain first and stress second is that in Excel, when you do a scatter plot, the first column by default is on the horizontal axis, and we always put strain on the horizontal axis. So let's calculate strain first. I just need to take my, remember the definition of strain is delta L over L. Delta L is my elongation. I need to divide it by my gauge length, which I put in cell B2. So I'm going to use $B, $2. So that when I copy this down, it'll keep grabbing that same gauge length cell and it won't go and use those empty cells below it. That's my strain. From here, I can click on that, tap on it, hit fill, and drag it down, and it will fill the column with strain values. The first one is 0 because when there's no elongation, the strain should be 0. Next, let's do stress. The equation is force over area. So first I'll plug in the force, which is in column A. I will divide it by the area. Let me put this in parentheses. I need pi, which Excel calculates for me with a pi and 2 parentheses, times the radius squared. So let me put in diameter. That's in cell B2. That's diameter, not B2, B1, diameter. And we need to divide it by 2 to get radius. And I need to square it, which is the same thing as multiplying by, again, $B, $1 divided by 2. If you know how to do squareds in Excel, go for it, but I honestly can't remember. So this will work. And then I need to close parentheses so that it's all happy. And stress should be 0 because the load is 0. Now I'll come up here, use the fill function, and now I've got stress values. So to plot this in my Excel app, I select all of those that I want to plot. I come up to the top to hit insert, charts. I like a scatter plot, and I like to keep the dots on it. So I'm just doing a scatter plot that looks like that. We can make it a little bigger, maybe a little too big. And that's what I get from Excel. What do we see? We've got an initial linear elastic region, followed by something interesting that happens somewhere around 60 KSI. And then the stress increases quite a lot before dropping off at the end before failure. I already did this before, and I copied these things over into Notability so that I can mark them all up and grab all the data that I need. So let's go over to Notability and finish the problem. So scrolling down to my page where I put my chart in and my stress and my strain values. I'm not going to do these in the same order that the problem asks because I like doing things a little differently. Let's start at the end. Fracture stress. Well, that is the stress right here at the end when it fails. We didn't actually need the plot to do this. We just need to do the calculation. So for that, I'm going to grab this last row, and there is my fracture stress, 93.1 KSI. And I got my fracture stress. Next, let's do ultimate stress. That's the biggest value that we measured. So let me do this. Actually, let's do this one with a different color. Let's do red. Ultimate stress. That's the biggest value we measured. So looking on this chart, it looks like it's this point right here for my ultimate stress. So that is going to be this third to last row. It's the biggest stress value we measured. And that comes out to be 108 KSI. That's my ultimate stress. And one thing I'm going to say, because I am an experimentalist, this is not very much data. And if I were trying to actually measure the ultimate stress in a material, I would not like this data because we went a long time before collecting data points. And how do I know that the stress didn't hit 110 or 115 or 120 before or after this point? So this is kind of sparse data. So we'll say maybe it's approximately equal to that. And same thing with the fracture stress. Who knows if that's really the stress when it fractured? Might have been a second before or second, well, I guess it wouldn't be after. But these are approximate values based on some data. Yield stress and Young's modulus are the other two things that we need to calculate. So let's pick another color. Young's modulus, let's use purple. Young's modulus is the slope down here in this really steep region. That slope is Young's modulus. I'm not going to try to curve fit it. It's more or less a straight line early on in the problem. So what I'm going to do is just grab, you'll notice the first point on the line was 0. So why don't we grab a point, maybe come along here up to this point that's around 40 KSI. And if I just use those 2 points, I can use rise over run to get the slope. So my Young's modulus, you'll remember that, or let's remember Hooke's law for a second. Hooke's law said stress is Young's modulus times strain. That's the equation of a straight line through the origin with a slope E. So if I want to solve for E, E would be stress divided by strain. So let's look at that data point that is around 40 KSI. That's this one right here. And I just need to grab the stress value, 40.2591 KSI. And the strain value that corresponds with it is 0.00125. So I calculate that. And let me see what I get. 32,207 KSI. Now that is way more precision than we actually know. I'm going to say it's approximately 32.2 times 10 to the third KSI. I mean, all of these are approximate because we don't have tons of data here. And then we had one thing left. We found everything except for the yield stress. Okay, yield stress is a little bit of a tricky one. To find yield stress, what we do is, because it's a little bit fuzzy what's happening in this region, it's curving, it's departing from linearity. It's usually the stress is, the strain starts changing dramatically quickly. So the way that we have defined yield stress is we come over here to a strain of 0.002. And we just pick that because it seems to work really well for a lot of materials. We come over to 0.002, and I'm going to tell you I've already drawn it too far to the right on the curve. And then we go up and we find the stress level where it intersects the curve. And we define that as our yield stress. So I can't see it very well on the curve. I'm going to look at the data instead. And you'll notice I have 2 data points that are close to 0.002. Is these 2 data points right here. They aren't exactly 0.002, but that 00175 is pretty close. The yield stress is probably just a little bit higher than that 55 KSI, but it's not going to be as high as 59. So we're not going to get an exact number. Again, I would be critical of this data because there aren't enough data points to get a good value for the yield stress. But with the data we have, I would say that the yield stress is somewhere between 55 and 59. Should we call it 57 KSI? Good enough. I wouldn't mark you wrong if you put 55 or 59 or 56 or 57. Anything in that range is as accurate as we can get it with this data. So we have found a plot of the stress strain curve, which it asked us to. We did that by taking our load data, dividing by area to get stress, our elongation data, dividing by original length to get strain. And then with all of that data, we proceeded to calculate fracture stress. That's the stress at the very end of the test when the specimen breaks. The ultimate stress, that's the peak measured engineering stress, which happens sometime before fracture typically. Hooke's law we then used to figure out the Young's modulus. That's the slope of the curve in that initial linear elastic range, and we estimated that that's about 32,000 KSI. And finally, we found an estimate of the yield stress by using the standard that we go over to a strain at 0.002, also called 0.2% strain. And we roughly estimated that the stress at that point is around 55 to 57 KSI.